I'm Rainer, and this week we're going to be doing a problem where we've got a ball that starts off rolling at some speed v naught, and this ball has mass m, radius r, and it's a uniform sphere, and we just want to know how high it goes. And so when I see stuff like this, when I see a ball rolling with some speed, and I want to find height and stuff like that, and I know gravity's acting, this is just jogging a bunch of work energy ideas into my mind. Because I know these can be related to like kinetic energies. We can have like a change in potential energy or maybe work done or something by gravity, and I can see it all coming together. So let's just go with it and see what happens. So the first thing to do is pick a system. And we've got plenty of choices, but one that I like to make is to choose everything to be the system. Because then it keeps everything straightforward and I can do problems in a similar way every time. So let's make everything the system. Now, we'll just go ahead and apply the work energy theorem. So, I'll say work equals change in energy for this system. I know for a system of everything, there's no external forces. And so, work is only done by external forces, so I have none, no work, 0. Now, the changes in energy. I know a ball speeds up, it gets rotating faster, and so those look like two kinetic energies. So I'll have a delta KT, delta KR, and then I'm going to have Earth and the ball in my system, and they're going to increase distance away, so I know I'm going to have a delta UG. And that's all I can think of. So we can go ahead and start plugging in. We can say, I know delta KT is 1/2 mv final squared minus 1/2 mv initial squared. Well, v final in this case is, well, let's go ahead and pick those. Initial time, I'll say, is when we first start. Final time is at the very end when we stop. And we'll say height at the end, which is what we're looking for. We're looking for how high it goes. Will be the height of the center of mass. That's what we'll care about. So, at this point, I'll say 0 equals. V final goes to 0, so we're just left with the negative 1/2 mv initial squared. Then, delta K rotational. I know that's 1/2 I omega final squared minus 1/2 I omega initial squared. And similarly, omega final is 0 because it stopped. So, minus 1/2 I omega initial squared. And then delta UG, I know is just mg times the change in height. So I'm going to say plus mg, and then I'm going to say, well, final height is h, and that's the final height of the center of mass, and the initial height of the center of mass is sitting off the ground by a radius, right? So what it's really going to be is final height minus initial, so h minus r. And now, at this point, we're really close, because we've only got a couple more unknowns, and we can just go ahead and solve for those in another way. So I know I for a sphere is 2/5 mr squared. And luckily I know m and r, even though those turn out not to matter. It's kind of cool. I'll say 2/5 mr squared. And then omega initial, I really know it's just v initial over r in the case of rolling. So that's really just vi over r. So as a result, if I plug those in, I'm going to get minus 1/2 m v initial squared minus 1/2 times 2/5 gives me 1/5, and then m, and then this vi squared over r squared, this r squared will cancel with this r squared, and I'll just be left with a vi squared. Then I'll have plus mgh minus r. So notice I can divide everything by m, because there's 0 on this side. 0 divided by m is still m, and we're just left with a little bit of stuff. So at this point, we're looking for h, and we know r, we know g, and we know v initial. So we've got one equation and one unknown at this point. So we can just solve this equation, and I I will leave that as an exercise for you. So that's it.